number of data points or the number of people in the survey. And P is the proportion, and we usually say the proportion of successes. For example, if you were asking a yes-no question, the number of people out of the total who answered yes would be the proportion of yeses or the proportion of successes. Similarly, we say 1 minus P is the proportion of failures, or in the example I gave, the proportion of people who answered no. The other formula we're going to be working with is the z-score formula. So the z-score tells us how many standard deviations a particular statistic is from the population proportion in a normal distribution. So here's the formula. We're going to take statistic, which is going to be the sample proportion, the P with the hat, and subtract from that the parameter, which is the population proportion, and then divide it by the standard deviation. We'll also see later on in situations when we're calculating the standard deviation, this formula up here, if we don't know the population proportion, we'll use that sample proportion P with the hat and call it the estimated standard deviation. So example 1 is about predicting colors in M&M candies. So in class, students would count out 60 M&M candies and then think about what proportion of blue M&Ms are in the total M&Ms. So in this case, the sample is the number of blue M&Ms out of the 60 on your plate, meaning an individual student's plate. That's a sample because it's part out of all of the M&Ms. The population is all blue M&Ms made at the factory that we're trying to make the prediction about. So we're asked, does our variable x represent categorical or quantitative data? So in this case, x is categorical data because we're looking at the M&M color. And so because that, you'll use the sample proportion p hat. If we were working with quantitative data, you'd use x bar, the sample mean. But with categories, we can't average categories, so we use the sample proportion. So in this case, it's going to be the number of blue M&Ms out of the 60 total M&Ms that each student has. So if we were doing this in class, each student would have 60 M&Ms, and they'd count the number of red, green, blue, all the different colors, and then figure out the proportion out of 60. So for example, 10 out of 60 red would be 1 out of 6 reduced. And so different answers are going to come up in different groups because we're sampling. So when we sample, we don't get the same results, but overall we should get similar results, especially if we take very many samples and look at the data from very many samples. Question D asks, would you expect all of the sample proportions of blue M&Ms to be approximately the same? Why or why not? So we do expect each group to have different sample proportions because of variability in samples. So variability is the change in samples. Again, we're not going to expect every sample to be exactly the same because we've got this random selection of M&Ms going on. So samples are going to have variability or differences, but overall we're going to see some trends. Question E tells us, typically statisticians cannot know the population proportion, but the M&Ms folks claim that they produce an equal number of each of the 6 colors of M&Ms. According to the M&Ms folks, what is the population proportion P of blue M&Ms? So if M&Ms produce an equal number of each color, then we expect 1 out of 6 to be blue, and our population proportion P is 1 out of 6. If we were in class, each group could write their sample proportions up there and see how this compares to that population proportion 1 out of 6. And you'll notice some groups have more than 1 out of 6 proportion blue M&M, some groups have less than 1 out of 6. So again, we expect there is going to naturally be variability in the samples. Question G asks you to use the expected number of successes formula. So that is saying the expected value or the expected number of successes, in this case a success is a blue M&M, is the number of M&Ms times the proportion that we expect to be blue. In this case, we're working from the population proportion. So 60 times 1 out of 6, we can say that's 60 out of 6 or 10. So if you had 60 M&Ms total, you'd expect there to be 10 blue M&Ms according to the population proportion. Now we know in reality, due to variable and chance, it's not going to be exactly 10 for every group. The expected number of failures formula in our vocabulary list is going to tell us the expected number of not blue M&Ms if you've got a sample size of 60. So 1 minus the proportion for the population is 1 minus 1/6, or 5/6. And so our formula n times this 1 minus p is 60 times the 5 out of 6, or 50. So we would expect 50 of the 60 M&Ms to be not blue according to that population proportion. So now we need to check, can we use a normal distribution to model this data? And so the normal distribution formula says that if the expected number of successes and failures is 10 or more, we can approximate our model with a normal distribution. So in our calculations above, we had an expected 10 successes or blue M&Ms and 50 expected failures, not blue M&Ms. So yes, we can use a normal distribution since both n times p, that was our expected number of blue M&Ms or expected number of successes, was greater than or equal to 10, and n times 1 minus p, our expected number of failures, or we would say not blue M&Ms, is greater than or equal to 10. This idea of successes and failures is just really putting into two groups the different types of M&Ms. And in statistics language, we call them successes and failures, but it doesn't necessarily mean that the not blue is a failure. It's just the language we use in statistics. So if we are looking for blue M&Ms, we call those results successes, and then anything that's not blue is considered a failure or not counted. So now we're going to use the standard deviation formula from the previous section. So we've got p times 1 minus p divided by n, and then we're going to square root all of that. And this is going to be the population standard deviation using this assumed population proportion. So we've got 1 out of 6 times 5 out of 6 divided by 60, all square rooted. So you can check on a calculator. That works out to be 0.048 for the standard deviation, or approximately 0.05. So now we want to look at this on the normal distribution. So using our population proportion 1 out of 6, we can say 1 out of 6 is 0.0167 as a decimal, and then we can use that standard deviation rounded to 0.05. So in the center of our normal distribution, we put the 1 out of 6, or 0.167, and then we go up by increments of 0.05, our standard deviation. So we go up 3 standard deviations. And then we go down increments of 0.05 to go down to -3 standard deviations. So in class, if we had gotten a class proportion, when we put together all the M&Ms in class, sample proportion p hat of 0.18, that would be right here in the normal distribution. So between the center and +1 standard deviation. So this actually seems like it might be reasonable. It's within 1 standard deviation, so within where we expect 68% of the data to be. If we want to calculate exactly how many standard deviations away from the population proportion p the value is, we use this z-score formula. So z equals p hat, the sample proportion, minus the population proportion divided by the standard deviation. So we take that sample proportion, 0.18, subtract 0.167, the population proportion. This is just 1 out of 6 as a decimal. And then divide it by 0.05. So remember, with fractions like this, you do the subtraction on top first and then divide according to order of operations. And so we get 0.26 standard deviations above the center. So this seems like a very reasonable value. So I would argue, because we're within 2 standard deviations, that it is possibly true, the claim that the M&M's factory makes. We can't say for sure that it's true, but it looks like there's evidence that the true proportion of blue M&Ms could be 1 out of 6 from this sample data.